Subscribe to this channel for real-time video updates. The applications of the electrical properties of solids are numerous. Copper and aluminium are the most commonly used metals in electrical wires. Nickel is another metal used in making batteries. Semiconductors are other types of substances which have numerous applications. Today's discussion is about electrical properties of solids. Based on the electrical conductivities, solids can be classified into conductors, insulators, and semiconductors. The electrical conductivity of conductors range between 10 raised to 4 and 10 raised to 7 ohm raised to -1, meter raised to -1. In the case of insulators, it ranges between 10 raised to -20 and 10 raised to -10. In the case of semiconductors, the electrical conductivity ranges between 10 raised to -6 to 10 raised to 4 ohm raised to -1, meter raised to -1. Now we'll see what are the reasons for these differences in electrical conductivities. Band theory of conduction. According to this theory, the atomic orbitals of metals forms molecular orbitals. You have learned about atomic orbitals and molecular orbitals last year. Now, when these molecular orbitals are formed, their energies are so close to each other that they form a band known as the valence band. In that valence band, there are electrons, the valence electrons of the metal. So, the molecular orbitals of all the atoms in the metal forms an energy band known as the valence band. And beyond this valence band, there is yet another energy band which is known as the conduction band. The valence band is filled with electrons, but there are no electrons in the conduction band. So if you look at this figure, you can see a violet colored shaded portion marked as filled and an ash colored shaded portion written as empty. So the filled band is the valence band and the empty band is the conduction band. Normally, in the case of any substance, the valence band will be filled with the valence electrons. When these substances are in the vicinity of an electric field or they are under the influence of an applied electric field, electrons will move to the conduction band from the valence band, and that is how they are able to conduct electricity. In the case of metals, electrons can easily jump to the conduction band as there is no energy gap between the valence band and the conduction band. They are almost overlapped. But in the case of semiconductors, there is a small energy gap between the valence band and the conduction band. And in the case of insulators, this energy gap is so large that the energy gap is known as a forbidden gap and electrons are not able to jump to the conduction band. In the case of semiconductors, few electrons can jump to the conduction band, especially when there is an increase in temperature. But in insulators, no such possibility is there. So this is band theory. Now we'll see more about semiconductors. Semiconductors are usually elements belonging to group 14. Example, silicon, germanium, and they are known as intrinsic semiconductors. Even though they are conducting, the extent of their conductivity is very low. It is not useful for any practical purposes as the current generated is very less. Hence, what we do is we add certain impurities to these intrinsic semiconductors and makes them extrinsic semiconductors. Extrinsic semiconductors have increased electrical conductivity and they have various applications. So the process of adding an impurity to an intrinsic semiconductor so as to increase its electrical conductivity is known as doping. Doping produces two different types of extrinsic semiconductors, Ntype and Ptype. Now we'll see what are Ntype and Ptype semiconductors. Ntype or electron-rich semiconductors. So here we have a crystal of germanium. In germanium crystal, you can see a phosphorus atom inside. N-type or electron-rich semiconductors are produced when a group 14 element is doped with group 15 elements. That is, an element with 5 valence electrons. In the germanium crystal, you can see each germanium atom bonded to 4 other germanium atoms using 4 electrons. But when the phosphorus impurity is added, phosphorus has 5 electrons. So, phosphorus forms 4 covalent bonds with 4 germanium atoms, but there is an excess electron due to its 5th electron. So many such phosphorus atoms will be present throughout the germanium crystal when it is doped, so that a large number of electrons result in the crystal. These electrons are free to move and hence increases the electrical conductivity of germanium or silicon. So this type of electrical conduction is known as N-type or electron-rich semiconduction, and it has got a lot of applications. P-type semiconductors, otherwise known as electron deficient semiconductors. When the semiconductors, intrinsic semiconductors, are doped with group 13 elements having valency 3, the resulting semiconductors are known as P-type semiconductors. Now look at this figure. This is a crystal of silicon atom. You can see boron at the center of this crystal. Boron has only valency 3. It forms 3 covalent bonds with 3 silicon atoms. But the 4th bond is not strong enough due to the shortage of 1 electron in boron. So there is an electron hole here. So in order to compensate this deficiency in electron, when an electric field is applied to this semiconductor, an electron from a neighboring atom moves to this position of the electron hole and occupies that position. This in turn results in an electron hole in the neighboring site, and this hole is again filled by another electron from another neighboring atom. So this process of electron movement occurs in a single direction, and the electron holes will appear to be moving in the opposite direction. So we feel that the electron holes are moving towards the negatively charged plate and the negatively charged electrons moving towards the positively charged plate. So this is how the electron deficient crystal increases the semiconductivity of the intrinsic semiconductor. Next, we can see the applications of N-type and P-type semiconductors. They are used in diodes, which acts as rectifiers. What are rectifiers? They convert alternating current to direct current. So N-type and P-type semiconductors can be used to make a diode. This is a diode. This diode is used as a rectifier. Then transistors. Transistors is made by sandwiching an N-type semiconductor in between two P-type semiconductors or a P-type semiconductor in between two N-type semiconductors. So transistors, as you know, they are used to amplify audio and radio signals. The intrinsic semiconductors are group 14 elements with valency 4. Now, by combining group 13 and 15 elements or group 12 and 16 elements, you can make semiconductors. Compounds like indium bismuthide, aluminum phosphorus and gallium arsenide are compounds formed from group 13 and group 15 elements. They are highly effective as semiconductors. Examples for compounds made from group 12 and 16 elements are zinc sulfide, cadmium sulfide, cadmium selenide, mercury telluride. Look at these compounds. These are certain oxides of transition elements: titanium oxide, chromium dioxide and rhenium oxide. These behave like metals, and especially rhenium oxide, rhenium trioxide, its appearance and its electrical conductivity is similar to that of copper. And these oxides, vanadium oxide, vanadium dioxide, vanadium trioxide and titanium trioxide, shows metallic or insulating properties depending on the temperature. So to summarize today's session, we had classified solids based on the electrical properties into conductors, semiconductors and insulators. We learned about the band theory and we learned about the different types of semiconductors, the N-type and P-type semiconductors and their applications. So this is all in today's session. Thank you. Subscribe to this channel for real-time video updates.